Last time we started section 3.5, and we had gotten to the point where we were going to take a look at basically some application problems using multiplication and multiplication, division, addition, and subtraction. The first one we're going to look at is Xuan. So Xuan saved $5,340 in 3 years. If he saved $95 per month in the first year and a fixed amount per month during the last 2 years, how much did he save per month during the last 2 years? All right, so what do you, looking at this problem, think you might do as your first step?
Subtract the 95 from the 5,340.
Not quite, but you're close. We will need to do subtraction, but I don't think it's 95 we want to subtract. Careful on what that 95 times 12. So the first thing was he saved $95 per month for a year. Okay? So we need to figure out what 95 times 12 is. So this is one option that one operation that we're going to have to do. After we get that figure, don't jump the gun and use the figure here, Jess. But once we get that number, then we're going to do what you suggested, Amy, is we can subtract that away from how much he saved total. All right, so just for some practice, let's do lattice multiplication for this. Okay, so the way that lattice multiplication works is you put one of the numbers along the top and one of the numbers along the right-hand side. And you're going to multiply and place the values inside of the lattice grid. So 9 times 1 is 9, goes in the bottom right-hand corner. 5 times 1 is 5, bottom right-hand corner. 9 times 2 is 18, so this goes 1 on the top and 8 on the bottom. And then 5 times 2 is 10, so 1 on the top and 0 on the bottom. After that, you extend your lines, your diagonal lines, and you add starting in the bottom right-hand corner. This is a 0. The next diagonal is 8, 1, and 5. What is 8 plus 1 plus 5? 14. So we write down the 4 and we carry the 1, and now I have 1 plus 9 plus 1. 11. If you want, you can simply write the 11 here because there isn't anything in the next column. If you really want to write down the 1 and carry the 1, that's okay as well. This is the value of how much he saved during the first 2 years, or first year. Okay? So the next thing we're supposed to do is we're supposed to figure out then, okay, well, how much did he save then during the last 2 years? So 5340 was the total amount he saved. And 1140 was what he saved the first year. This is actually a very nice subtraction problem. Why? There's no borrowing. So we don't even have to think about like what options we really need. Can't do equal additions, can't do anything because it all doesn't require borrowing already. So if I subtract, what do I get? 4,200. All right, now what am I going to do? We're going to divide 4,200 by 24. Why 24? Because it's 2 years and there's 12 months per year. So this is one of those places. Let me make a comment real quick before you start doing this the way you're familiar with and comfortable with. This is one of those places where you probably do not have division facts by 24s or multiplication facts by 24s stored in your brain. I don't. I mean, I don't know multiplication times 24s, and since I don't know multiplication times 24s, it makes the division more complicated. Sometimes you guess, even in the standard algorithm, you guess a wrong number. You say 24, well, I think that goes into, and this isn't a great example, but I think that goes into 42 twice. Okay, and you try it and you're like, oh, it wasn't twice, it's too big. You guys know what I'm talking about, right? So this is a good example for where the repeated subtraction sometimes comes in helpful when you don't have the multiplication fact committed to memory. So let me show you the repeated subtraction one more time because, again, we haven't done this now in a week almost, right? It's been almost a week. Repeated subtraction takes the value that you're multiplying, or you're dividing by, and you multiply it by powers of 10. So things like times 10, times 100, times 1,000, times 1, okay? And you want to multiply it by the biggest thing that will work. So in this case, the number is 100, right? 100 times 24 gives me 2,400, and I can subtract 2,400 from 4,200 to give me what? Uh-huh, 1,800 is correct. Okay, 1,800. All right, I can't subtract another 2400 though, correct? So the next thing I would do in repeated subtraction is I would take 24 times 10. All right. So that would be 240. All right, so what's 1800 minus 240? I don't have this method written in my notes, so you guys are going to have to. 1,000 what? 560? Okay, cool. Can we subtract another 240? Yeah, we can. So we've got another 24 times 10. Okay, so we're just practicing this method. I wouldn't necessarily have done the problem on this method on this problem, because you notice we're going to subtract 240 quite a few times, aren't we? What fun! All right, what's 1320 minus 240? We're still over 1,000. The 1080? Yeah? Okay, can we subtract 240 again? We can. Is it 840?
Yeah.
Okay, good. 240 again? Yes. I'm at 600. 240 again. All right, I feel like we made a mistake somewhere because we should be ending up with 0 at the end and we're not. So everybody check your subtraction. Somebody told me something along the way, or I did something along the way that wasn't quite right.
Wait, how do you know it's wrong right now?
Because if I subtract 240 again, I'm not going to end up with 240 left to get an even number. And I know it works out evenly, partly because of the setup of the problem as it's worded, and partly because we're working only in a whole number system at the moment. Where's my error, guys? Let me find it.
I think it's right.
It's right.
Are we okay? Okay.
It works.
Oh, I know why. I'm not to the point where I've subtracted any 24s. That's why. I'm sorry. Okay, we can subtract 240 one more time. What am I going to get? 120?
Yeah.
Okay, very good. I forgot about subtracting my 24s for a moment there. So I can do 24 times 1 then, right? So what is 120 minus 24?
96.
96. Can I subtract 24 again? I can. Leave me with
72.
72. Can I subtract it again?
48.
Oh man, hang on, that's not what I want to do. Who loves repeated subtraction? All right, try one more time here. I didn't make it want it to be that tiny. Now I can't read anything. Okay. All right, 24 again, right? 48, 24 again. And there's the 0 I was wanting. Okay, does anybody remember how to figure out what the answer is from all this crazy subtraction? Good. You add up all these tens and ones and hundreds. So there's 100. How many tens are there?
7.
There are 7. And how many ones are there? There are 5. And the answer to the question said, how much did he save per month during the last 2 years? So what should I write beside the 175? Dollars or a dollar sign, right? Because this is the actual units on this particular answer. $175 per month. Okay, so the setup itself is not where you have the different options of methods. It's actually in doing the different pieces of the setup that you have the options of the methods. All right, let's try another one. Dan has 4,520 pennies in 3 boxes. he says there are 3 times as many pennies in the first box as in the third, and there are twice as many in the second box as the first. How much money does he have in each box? So what do you think you might do first as you're looking at this problem?
Figure out an equation.
You might be doing an equation. I would probably do one thing before I did an equation.
Draw some.
I would probably be tempted to draw the boxes to kind of get my head wrapped around all the pieces and make sure that in my mind I've got the right location for the right pieces. So we'll call this as box 1, 2, and 3. And then let's figure out, we know that if we add these boxes together, they have to add up to 4,520. But let's figure out what we're adding together. It's not the 1 and the 2 and the 3. Those are just labels for my boxes, right? It's like saying the boxes are, you know, Stan, Roger, and Jeremy, or whatever, okay? They're not numbers, really. It says, he says there are 3 times as many pennies in the first box as in the third. So what might I want to do to get that relationship established correctly?
Use an X.
You might use X. So where would I put an X, Emily, or where would you like to see me put an X?
So like 3x for the first box, there's 3 times as many, and then do x for the third box.
Okay, so if there are X pennies in the third box, then there would be 3X pennies in the first box. Is everybody good with that? All right, then it says, and there are twice as many as in the second box. Excuse me, as in the first.
So 2 like 2 times 3 is 2.
Yeah, it would actually be 2 times the 3X, right? Because it's supposed to be twice as many as in the first box. So this actually ends up giving me 6X, yeah? Okay. Now that I've got the relationship established using variables, what would I do?
Right equation.
Okay, so what would the equation look like?
3x
So just
plus
adding those two.
6x plus x equals 4,000.
Okay. Is everybody good with that? Yeah? Okay, great. All right, so then what do I have on the left?
Combine the x's.
Well, we're going to combine the x's, and it's a nice, wonderful number 10. What would I do next?
Divided by 9
I would divide by 10.
on both sides.
And what is 4,520 divided by 10? 452. Now, what is 452?
No, it's the x.
Pennies. It's a number of pennies, right? It's the number of pennies in box 3, which is some of what some of you were telling me. Right, so there are 452 pennies in box 3. Let's go back to what the question asked us to find, though. It asked us how much money does he have in each box. So how much money, then, is the question for each box? All right, so we've got box 1, box 2, and box 3. And we know box 3 is $4.52. What do we need to do next, or what could we do next? Right, we could take that and you could do it either as the dollar amount and then change it, or as the number of pennies and then change it. We want to multiply that by 3. So we'll just use a standard algorithm on this. 2 times 3 would be 6, and then 3 times 5 is 15, and we carry the 1 for that awkward addition happening in the middle, of course. 3 times 4 is 12, plus the 1 is the 13, right? So in box 1, I have not $13.56, I have $13.56, right?
How are we able to just like put in the decimal where we like?
Because a penny is equal to 1/100th of a dollar.
Okay.
It's because they chose pennies in this
If
diagram.
they done nickels or something.
Yeah, it'd be much messier, right? Yeah.
Yeah.
It's because the pennies have that nice relationship. If we did dimes, we'd have a fairly nice relationship as well. The coin wouldn't have exactly sort of disappeared, but it would have been 1 decimal point off instead. How do I find box 2? Yeah, we could actually take that last value, 1356 times 2. That's a friendly enough way to do it because we knew it was twice as much as box 1. So 2 times 6 is 12, carry the 1. 2 times 5 is 10, make 1 and is 11, carry the 1. 2 times 3 is 6, plus 1 is 7, and then 2 times 1 is 2, for a total of $27.12. All right, any questions on that one? Okay. A student observes that 39 plus 41 is equal to 40 plus 40 and asks if 39 times 41 is equal to 40 times 40. How do you respond? Now, notice what happened on the first argument, if you will, their first claim. What they did is they added one to one number and took one away from another number, right? That's actually a method we have. It was called the trading off algorithm. Do you guys remember that one? It was sort of like equal additions. Not exactly, but similar. And so they're actually wondering, basically, is there an equal additions algorithm for multiplication? That's kind of what they're asking about. So very concretely, how could you find out if the student, how could you find the most direct answer to the student?
Have them multiply it out.
Yeah, just multiply them out and see, right? I mean, like, that's actually something that we could do. So let's do what the student's actually asking us to do, which is finding out whether or not 39 times 41 is equal to 40 times 40. And I like 40 times 40 much better. So if this worked, we could definitely do this all the time, right? We would want to, because 40 times 40 is lots easier. All right, so let's do the 39 times the 41. So if I do times 1, I get the 39. And then I get that funny, mysterious 0, because I'm not really going to be multiplying by 4, but by 40. What is 4 times 9? 36. So we're going to carry the 3. 4 times 3 plus 3, 15. And if we add these values together, we get 1599. What happens when I do 40 times 40? You actually get 1600. So the actual answer to this question is no, they're not the same. But it is interesting that they're so very close together, right? I mean, that's 1 apart. So isn't that interesting? So another student sees your response, and they notice then that 39 times 41 is the same as 40 times 40 minus 1, right? It's only 1 off. As much as you may like to multiply 39 times 41, we all agreed that it's much easier to multiply 40 times 40 and just subtract 1, right? So that would be a nice feature if it were always true. So the student also notices that if you do this with 49 times 51, you change that to 50 times 50 and subtract 1, you get the same answer. And so they want to know if the pattern continues. And if it continues, what is the relationship that has to exist between the first 2 values in the equation for this to actually work? So take a look first at the kinds of values that they're picking. Can you sort of see what they mean by a pattern to continue? Tell me what relationship you notice between the 2 values that they're choosing on the left-hand side, the ones that I've underlined. Yeah, the second one is 2 higher than the first one. So we might be led to think that if this in fact works, it's probably because they're 2 apart. But it also simply might be that they're each just finding the difference between them and it's halfway, right? So it also could be like, okay, well, let's say they were 4 apart. Maybe they would work if they were 4 apart and we just took the halfway point between them. So like maybe this would happen and it would work if it were 38 and 42. And we split the difference at 40. That's what we're kind of trying to explore. So what I want to show you is how you could actually explore what this relationship looks like. So it looks like, to start with, that they have chosen values, like you said, that are 2 apart. So if one of them is x, then the other one is x plus 2. And they're multiplying them together. Right? 2 numbers are multiplying and they're 2 apart. One of them's x, the other's x plus 2. If you multiply these together, what do you get? X squared plus 2x. Very good. So this is sort of the left-hand side, LHS. Now we're going to do the right-hand side. The right-hand side says, okay, we're going to take the x and the x plus 2, and we're going to split the difference. So what's halfway in between them? What's halfway between x and x plus 2? X plus 1. Yeah, so like if you're thinking on a number line, if you have x, and then you have something, and then you have x plus 2, the one that's in between was x plus 1. Okay, so if you take, or if you can think about it as adding 1 to one of them and taking 1 away from the other. And we want to know if this is always 1 more, that is, if I do subtracting 1, if this always is going to work. So we're going to multiply x plus 1 times x plus 1 together. If you remember order of operations and foiling and all of that good stuff and distribution, you have x times x is x squared. That's the first terms. The outer terms, x times 1 is x. The inner terms, 1 times x is x. And then the last terms, 1 times 1 is 1. Okay, so hang on. I had an x and then I needed a 1. There we go. Too much going on. And then I had this other minus 1 out here at the end. Okay, so if I combine like terms, I have x squared and then what? 2x. And then the plus 1 minus 1 cancel, right? So this actually does always work if the two numbers are 2 apart. All right? So this will always work. If the numbers are 2, or let's say differ by 2. Now, I'm not going to go into the details of what you could do, but if you wanted to know if they would work if they differed by 4, could you do it? Yeah. What you would do is you would go up in here and you would change this number 2 to a 4. X and x plus 4. And this one where I have x plus 1 and x plus 1, I do x plus 2 and x plus 2, because plus 2 is halfway between the x and the x plus 4. And you'd multiply them out, and you'd find out they don't actually differ just by 1. It's by more than that. They would differ, I think, by 3, if I'm remembering how you would think about it correctly. So it really is something unique to the two numbers differing by 1 value apart, well, 2 values apart, but then 1 value apart when you find the halfway point. All right, last thing we're going to do is we're going to do a little bit of mental math. We talked about last time that, in fact, when you do mental math, you actually have to show me what you're doing, because otherwise I can't see it, because I can't see inside your brain, unfortunately. Wouldn't that be cool if I could? Like for math only, of course, for math only. All right, so let's take a look at some different methods for mental math for front end, for multiplying. All right, so the first one is front end multiplying. And so front end multiplying does the following. What it does is it multiplies each of the values times the second value, each of the digits by the second value. So basically what it does is it takes 46 and it breaks it apart into 40 and 6. And it multiplies each of those individually by 5. So 40 times 5 is 200, and 6 times 5 is 30, and those added together is 230. And I think realistically you could probably do that in your head. It's just a 2-digit number by a 1-digit number, right? You may not want to do that in your head, but it's reasonable to think that somebody could, correct? Yeah. If you had a 3-digit number times a 2-digit number, this would not be a reasonable way to do this problem. You're not going to do a 3-digit times 2-digit in your head by breaking it apart like this. But for small values, 2-digit by 1-digit, it works. Compatible numbers. We encountered this one last time as well, or in the last section as well. Compatible numbers is the idea of taking values that, and when we were doing addition and subtraction, added to nice numbers together. This one is multiplication, so they multiply to nice numbers together. So what numbers here would multiply to something that's super friendly? 5 and 2 are fantastic. What do they multiply to? 10. They're great. So I'm going to group a 5 and a 2 together to get a 10. What else might multiply together nicely? Either the 4 and the 5 or the 8 and the 5, either one, because they multiply to something that gives you a single-digit number with some zeros, right? So most of you told me 4 and 5, so I'm going to go with that one. What is 4 times 5? 20. So now I have 20 times 8 times 10, and it probably doesn't much matter what order you go in at this point, because everything is still fairly clean, right? So maybe you decide you are going to do 20 times 8 to give you 160. And then multiplication by 10 is like the best thing ever. So you get 1,600. Okay? It would not be helpful ever in this problem to multiply 4 times 8. Agreed? That is not one we would want to multiply together. Or 2 times 8, really, as the first step. Not a helpful step. Thinking money. This is really fantastic. Okay, so you guys are familiar and comfortable with using money because it's something you handle and work with every day, or at least you have on most days of your life. I mean, this is something you use all the time. So one way to do this, and of course it only works in certain situations, is to think about this 5 as a specific kind of coin. What coin would it be? It's a nickel. Okay, fine. I've got 46 nickels. That's how you're thinking about this, okay? I'll tell you what, 46 nickels is not near as nice as 23 dimes. Now, where did I get 23 dimes?
So you did 46 divided by 2.
Yeah, I did 46 divided by 2. Basically, I took every 2 sets of nickels and I turned them into a dime. Can you imagine doing that? Because what is 23 dimes? In terms of the next value, what's the value of it? All right, 230 is what I'm looking for. Nobody's saying, but I don't think I'm asking the question very well, apparently. 223 dimes is 230, right? Coins, or cents, 230 cents. Okay. Because a dime's worth 10, and 23 times 10 is much friendlier than 46 times 5. What in the world would the 25 be? It would be a quarter. What is easier to work with than a quarter? And do not tell me, thank you, dollars goes, don't tell me pennies. That's not helpful at all here. Yeah, a dollar bill would be much easier to work with here, right? So if I had 44 quarters, how many dollars is that? It's $11. Now, understand the dollars are worth 100, okay? I mean, we're really thinking money. We're not working really with money. So if I have $11, this would be the value 1,100. Because a dollar is worth 100 cents. We're thinking about everything in terms of cents. Okay,
So this
25
one's
cents, a dollar is 100 cents.
1,100 cents, and the last one was 230 cents.
Well, there aren't any units on the problems themselves. Do you see how this doesn't have any units on it?
Yeah.
So there's no units on our answer either. We're just thinking about it like we think about money. Breaking up the dividend. Okay, again, mental math works nicely sometimes and not so nicely other times. Okay, so I'm not telling you like this is a fantastic method to use in any and every situation. It's definitely not. But when it comes up nicely, it's really nice. And it's really nice on this particular problem. So if you think about dividing this one right here, this 9, this 6318 can be thought of as 6,300 plus 18. Everybody good with that so far? And the reason that's a nice breaking apart is because 63 and 18, respectively, are actually multiples of 9. They divide by 9 evenly. So what is 6,300 divided by 9? That would be 700. And 18 divided by 9 would be 2. So this is 702. So you're breaking it apart in the dividend.
Does that work with most dollars?
This one is probably your better bet right here, 425. So if you think about 425, 42 does not divide by 5, right? And it really, while we could break it apart into like 420 and 5, that'd be okay. There's a more natural break on this one. So if you were dividing by 5, part of it, to answer your question, Emily, is what you're dividing by, and then part of it's what you're dividing. Yes, ma'am.
It says on the notes this is using compatible numbers, so is this breaking
Yes.
it into-
Yes, it's using the compatible numbers for values that divide evenly into 5. But it works a lot like the breaking apart algorithm. It's just that you're breaking it apart into compatible numbers. For instance, things that divide nicely by 5. So 425, 400 divides nicely by 5, and so does 25. So 25 and 400 are compatible with 5 because they divide nicely. That's what makes them compatible, yeah. All right, so how many times does 5 go into basically 40? 8, so it's going to go into 400 80 times. And then 5 will go into 25 5 times. So this becomes 85. And I really think you could do that in your head. There's no reason you couldn't break that apart in this particular problem in your head. Now if the number's 437, we have problems, right? Doesn't work for everything. All right, do you see the key word here? What does estimation mean? Not exact. It means the answer that I get may not be exact. It could be, but the methods by which I'm going to do the problem are going to indicate that it's probably not going to be. But sometimes close enough is good enough, isn't it? I mean, really, it really is good enough sometimes. So, if you take a look at 386 and you multiply by 4, I mean, like, I'm going to have to multiply every single one of those. There's nothing that's going to give me nice zeros anywhere or anything like that, and I'm asked to do an estimation. So this is actually an example of front-end estimation. What front-end estimation does is it just uses the first 2 digits. So you're going to do 300 times 4, and you're going to do 80 times 4. And honestly, you're just going to ignore anything else. So this is a 4 or 5 digit number. You do the first 2 digits of it and you ignore everything else. So 300 times 4 is 1200. 800 times 4, I'm sorry, 80 times 4 is 320. 320, yeah, you're just off by a factor of 0 there, or the 0 at the end there. And then if you add these together, what do you get? Yeah, 1520, right? Right? Yeah, I think you're still off by a 0 there, Amy. And this is approximation, so you'll notice I put my approximate symbol. This is not the answer to the question exactly. Because, I mean, I can't really ignore the 6 and get an exact answer, but that's exactly what I did. I ignored the 6. Okay? So if something references front-end estimation, it's the first 2 digits that it's referencing multiplying by the other value. Yes, ma'am?
On like mental problems, like they're hard for me because I'm visual. So can I go ahead and like write it down?
You can, as long as you're using a mental math strategy to do it. In fact, you need to write it down or I can't see what you're thinking anyway. Yeah.
Okay.
But occasionally I'll have somebody do a problem that's supposed to be mental math, like
And I'll just do it normally.
like this problem, and they'll actually write down the whole problem, like longhand standard algorithm, and I have a really difficult time believing that was done in their head, right? Like that's not the point. So like on this problem, indicating that you're thinking with quarters here, you know, or that you're thinking money or something is actually necessary in order to be able to do this in your head. Okay, I think this is our last one, compatible numbers. Okay, again, we're still estimating, right? Okay, estimation still. So 4,132 is not compatible with 4, all right? But parts of it are not too bad, agreed? So you might look at that and say, you know what, okay, but I can take this 4,132 and I can break it down into a 4,000 pretty okay and a 100. And those are both pretty easily divisible by 4. And I can do that in my head. And, you know, maybe you even think the 32 is not so bad, but we're supposed to be estimating, so we're not intending to try to get an exact answer here. So this is really kind of good enough. 4,000 divided by 4 would give me 1,000. And if you really wanted to do the 100 divided by the 4, you could just stop at 1,000 and say it's about 1,000. 100 divided by 4 is another 25. So this is a 1,025. I'll tell you what, in my notes, my answer in my notes isn't 1,025. It's actually just 1,000. In my notes, I stopped at this step. 4,004, we're pretty close. I called it good. Okay? So there's a little bit of flexibility here that works out nicely.